Okay, in our last video, we mentioned that the leading term of a polynomial gave you the end behavior. And we briefly went over those rules, that a positive leading coefficient, you always start with that leading coefficient. And if it's positive leading coefficient, it tells me that the right end behavior is up. And if so, the leading coefficient is telling me about the end behavior on the right side of the graph. So anytime you see the limit as x is approaching infinity, that's really asking you about that right end behavior. And it's either going up, which would be code for positive infinity, or down, negative infinity. Okay? Now, the degree is going to tell me whether it's the same or the opposite. If we have an odd degree, then that's going to tell me that the left end behavior is opposite of the right. And if it's an even degree, that tells me that the left end behavior is the same as the right end behavior. So always check the leading coefficient first, then check the degree. But that kind of stuff is what we did in Algebra 2, and now we're just applying it to situations such, and I'm going to erase some of what I have written here. I just was using this as an example. You know, in example 2, we have something in standard form, and they're asking me for, they ask more stuff, but I'm just going to simply just ask, you know, what do you know about the limit as x approaches negative infinity? Well, the leading coefficient was a positive 1, so that meant the right end behavior was up. The degree was odd, so that meant that the left end behavior was opposite, so it was down. And since they're asking me for the limit as x approaches negative infinity, which would be on the left side of the graph, the answer has to be negative infinity. Now, I know I asked you that question out of the blue. That doesn't go with example 2. So, you know, I know it's an extra question. Okay, so I'll erase all this stuff so I can continue working on the notes here. But that gives you some good information. And let's go back and see what we have back here. Okay, so in example 1, they are simply asking me to describe how to transform the graph of the appropriate monomial function. Okay, so, you know, this is review going back to, you know, fireproof form. You've got a cubic function that's been moved 1 unit to the left, so we know it's over here, and it's got a, as many of you would tell me, it's a vertical stretch, right, of 4. It's really hard to see that kind of stuff on a graph because it's gonna, the sidewalls are gonna get really steep and it's gonna cut through. Then it asks me this. It says, compute the location of the y-intercept. Well, that's easy because every y-intercept in the universe has an x value of 0. So what is 0 plus 1 to the third times 4? Well, so that's 1. 1 cubed is 1, and 4 times 1 is 4. So that's the y-intercept. So it would cross at 4 as it's coming through. On the other question here, this is, if I put it in its fireproof form, we'd subtract the 5 to the other side, and then we would divide by the negative 1, equaling x minus 2 all raised to the 4th. So this is a 4th degree, right? We know that the 4th degree function looks like that, but we've moved this thing 2 units to the right and 5 units up. 1, 2, 3, 4, 5. And then we've got a reflection, so it is flipped over the, so it's going to be doing this kind of thing. Okay, not quite as flat as I made it out to be, but I'm just doing a quick sketch. So right 2 up 5, and then it got reflected, so it's opening down. And then the y-intercept, let's see, the opposite of 0 minus 2 raised to the 4th plus 5. Let's see here. That's negative 2 to the 4th. And don't forget that minus. That's 16. That's the opposite of, right? Because this part is 16 times negative 1. Okay. So plus 5, that makes negative 11. So it'd be way down there. Can't even see it there. But negative 11 is that y-intercept. And a little too hard for me to graph there. Okay. Next on the agenda, graphing combinations of monomial functions. Graph the polynomial function, locate its extrema. All right, this is time for us to reach out to that graphing calculator. So clear everything out, make sure all your plots are turned off. We worked on some data stuff in class, so we don't want any of those plots turned on. And so, let me pause this for a second. As I was saying, make sure that you have no plots turned on and no equations entered in there. And so then we're going to have our y equals x to the third using our caret symbol, which is right above the division key on the newer style calculators that actually raises it up, plus x. Make sure you graph something like this. Y equals x cubed plus x. I would always return to the standard window, so hit the zoom and go back to that standard window, zoom 6, and graph. That'll change it to the negative 10 to 10. This may or may not be the best looking window in the world. When I go back and take a look at this, I would like you to be able to think about pulling out factors. Now, why is that? Because I need you to see that there is a real x-intercept. There's a 0 right here. You know, that's our shorthand word for x-intercept at x equals 0. Okay, which made sense when you looked at the picture and you saw something kind of doing like this. That's a little bit different than y equals x cubed, but not much, you know, it seems. So, some of these things are not going to be the easiest things to tell. You can tell some things, but not other things. So you might want to be able to do some algebra to help you. And we will do more and more algebra and look at things that we can pull out without having to do that. Locate its extrema and zeros. Okay. There are no extrema, right? There's nothing going on here in terms of, you know, the maxes and the mins, right? The little hills, the little valleys, none of that. Explaining how it is related to the monomials from which it is built. So you're taking a cubic function and a linear function and adding them together. Two odd functions, and, you know, that's why it looks a little bit different than just a plain old x cubed function. When you change that to subtraction, go back into your equation and change it into subtraction, x cubed minus x. You know, now we're talking, if I pull out an x, I get x squared minus 1. Now, over here, algebraically, we had a sum of squares, which does not factor over the real numbers. But here we have a difference of perfect squares, and we know that factors over because we can break it up into x plus 1 and x minus 1. If you don't believe me or trust me, then you can you know, do your insides and outsides and see that those cancel out. That's why there's no middle term there. But we should know that the leading coefficient is a positive 1, right? LC equals 1. So the right-end behavior is up. The degree is odd, which means that the left is down. So that makes sense. But we have x-intercepts at 0. Now, how do I know that one? Well, that comes from here. We have over at 1. That comes from here. And at negative 1, that comes from there. Now, if you don't know how I'm getting those, you set the factors equal to 0 and solve. Now, if I take my end behavior and attach it on the graph, And you'll notice that I picked the outermost zeros because that's where it has to cross the x-axis the last time. And then think to yourself what's going to happen in between. Now, what we will talk about eventually, to remind you, is each one of these has an exponent of 1. Those are called odd multiplicities. Oh, I'm not going to have enough room for this. I'm going to have to erase multiplicity. Now, when something has an odd multiplicity, that means it cuts through the axis. Now, if it had an even multiplicity, and what we'll see more of later, is that it bounces off the axis, okay? And we'll talk more about that when we get to it. Now, it's going to do something like that. Located its extrema. Okay, so this is where we could actually go into the graph and look at this. We'll graph it. Probably going to have to zoom in a little bit. Now, there are several zoom features we could use. One of the zoom features we could use is the first one in the list, zoom box or Z-box. And I'm going to move my cursor around, hit the enter button. Notice that I'm opening, basically I'm creating my own window by dragging. And then when I hit enter, it's going to redraw the graph based upon that window that I drug around. Okay? And so now I have this window. And then, so, you know what happens if I have this? I'm going to really be mad if that x cubed, let's see here, x to the third. I don't like how it glares off the screen. And I'm wondering if it's that yellow, if that yellow is causing it to happen. And zoom, standard. Well, maybe not. Yeah, it's not happening. It's not doing anything for me. Oh well, I thought it would. Maybe, but it's just the glare. Okay, so now I've got my, if I'm looking for the relative mins and maxes, remember we always find the locals first. There's a local max, and there's a local min. So we can do the calculate maximum feature. Do the left bound, right bound thing. You just need to make sure your cursor is on the left side of that little hill, and it doesn't matter where as long as it's, and then when it's on the right side, you hit enter. If you want to guess, you can get the cursor close to the top there, but it doesn't really matter. It'll go find it for us. So there is your relative max. The relative max is the y value, remember, 0.385, and it's occurring at that x value. So if we were to, maybe I can freeze this. Use the yellow pen so it's easier to see. We could say that the relative max equals 0.385 occurring at x equals negative 0.577 approximately. You know, so just to understand that a relative max or relative min is a y value, just like a limit is a y value. Okay, and then we could do the same thing to find that spot right there. Not that we need to waste your time with that, because I'm pretty sure you can use the relative, you can use that minimum feature, kind of like we did the maximum feature. All right, next on our list. These are some of the common looking polynomial functions, but you know, we're definitely not limited to this. I mean, you know, eventually you can get all kinds of stuff going on here, but we're, you know, things going in the same direction kind of thing, all kinds of stuff. Those are different cubic functions that they've drawn. Obviously mine were not cubic functions. Maybe I should erase mine. See, these are cubic functions. These are typical quartic functions. You know, they have to go in the same direction, but they have some, you know, weird shapes to them at different times. But those are the common ones. So now we have our theorem about a polynomial of degree n has at most n minus 1 local extrema and at most n zeros. It could have less than that, but the maximum number of local extrema that it could have, so these are your local mins and maxes, would be 1 less than the degree. So the example we just had where we did something like that, we had 2. We had a relative min and a relative max, so those would be the locals, and that's 1 less than the degree. But that's at most. We could have less than that. Like the example before that, we had none. It was a 3rd degree polynomial, but we still had no local extrema. So we will get up to n minus 1, or 1 less than the degree, and we'll cross the x-axis. Remember, this is where we cross the x-axis because these are our x-intercepts. The most number of times that you can cross the x-axis is the degree of the function. Could we cross less than that? Sure, we could. Okay, but we can definitely cross the x-axis. The most number of times would be the degree of that polynomial. Okay, we've already discussed this. This is all review right here. I don't necessarily think you absolutely need to copy this down in terms of understanding it, but if it would help you, this is the end behavior stuff we described. Right end behavior, left end behavior. You know, focused on your leading coefficient. That'll tell me the right end behavior first. And then if your degree is odd or even, okay, what happens with the left. In fact, in both of these cases, we're dealing with an odd. You can see that these are both odds, whereas these are both evens. Okay, but once again, instead of memorizing pictures, if you understand, leading coefficient tells me the right end behavior, degree tells me whether it's the left end behavior is the same or opposite as the right. Then you can look at all these limits and see what happens with those limits. What's going on to the far right of the graph, what's going on to the far left of the graph. Okay. Graph the polynomial in a window showing its extrema and zeros and its end behavior. Describe the end behavior using limits. Okay, so this goes back to what we've done a few times now. We're going to focus our attention. Here, let's just do part B. We'll focus our attention on the leading coefficient. Yes, we can go to the calculator. We can find out what window fits for that. Not really sure that is the most important thing in all the wide world. If I was in a testing situation, I might even give you the doggone window because I don't want you wasting time trying to figure out what window works the best. But we should know that our right end behavior, because we have a positive leading coefficient, our right end behavior is up. And because we have an even degree, right, even degree, we should know that the left is the same. So if I ask you about the limit as x approaches infinity well, I guess they're using letter G, g of x, you would have to say positive infinity, right, because it's going up, 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 up. If I ask you for the limit as x approaches negative infinity, that's on the left side of the graph going, that would have to be negative infinity. Sorry, running into each other. Oh, why am I saying negative infinity? Caught myself. It's positive infinity. Says so in our work here. Even, it's got to be the same as the right. Glad I caught that. Whew. Finding the zeros of the polynomial function. So you need to be able to look at this kind of stuff. This is basic algebra 2 type stuff when we get to polynomials. So look for GCF. All right, GCF is first on my list. Greatest common factor. In this case, it's an x. Pull it out, and then look at what is remaining. And then, if you can continue the factoring process, it would make your life a whole lot easier. This will not always be available to you, but hopefully you'll see that it's x minus 3 and x plus 2. Just thinking through that, what multiplies together to give you -6, but adds up to -1. Okay, that kind of thing. So we should be able to look at this leading coefficient, know that the right end behavior, since it's a positive one, the right end behavior is up. Since we have an odd degree, the left is down. Okay, now how many times does it cross the x-axis? It looks like it crosses 1, 2, 3 times. It crosses at 0 itself, at 3, and at -2. Okay, remember, set the factors equal to 0 and solve them if you want to know what those points are. Attach your end behavior. I mean, folks, this is a generic sketch of a graph. This is not the most perfect thing in the whole wide world. Oh, by the way, I am doing more than this question is asking. 0, 3, and -2 were the answers to the question of find the zeros. But since these all, I'm just gonna, beat a dead horse here. Since these all have an odd multiplicity, that means it cuts through, cuts through, cuts through. Now, if you want to get real specific with, finding how high and how low those things go, then you need to find the relative extrema. But I'm not interested in that for this question. I just want the basic sketch, just kind of like we did in Algebra 2. This is where we start talking about multiplicity. Multiplicity is the exponent. If f is a polynomial function and x minus c to the m power is a factor of f, but x minus c to the m plus 1 is not, then c is a multiplicity of m of f. That's an interesting way to say that. Why in the world would they make... well, that is a weird way to say that. Basically, nobody would write the same factor multiple times and not put them together. Okay, yeah, that's kind of a dumb way to say it. It's almost like if I had, x minus 2 and x plus 3, and then all of a sudden I had an x minus 2 to the 4th. They want... Oh, no. I see what they're getting at. As long as you don't have another factor of that same, of a different size. Okay. Okay, I can boil it down into one thing. Take the highest power of a particular factor, and that is your multiplicity. That's the best way to say that. Whatever that degree, that exponent is, that's your multiplicity. Nobody's going to try to be tricking you with that nasty definition there. If a polynomial function f has a real zero c of odd multiplicity, then the graph crosses, right? That's what we say. We said it crosses. So it is cutting through the axis. Okay? If a polynomial has a real zero c of even multiplicity, the graph does not cross the x-axis. Okay? It bounces. Now, this particular even multiplicity was made famous from the Katy Perry song. I'm sure you're all familiar with it. I kissed the x-axis and I liked it. Okay, it's where you end up with something where it ricochets off like this. This is what they're talking about. It's got an even multiplicity. So for instance, this particular polynomial in its factored form might be x plus 1 squared times x minus 2. Okay, so this is a third degree polynomial. It has a leading coefficient. How do I know what its leading coefficient is? Well, I designed it so that it would be x squared times x to the first. Well, what is x squared times x to the first? Well, that's x to the third. So I knew that the right end behavior would be up and the left end behavior would be down. But by looking at this, you can see that I have a -1 for my x-intercept on the left and a +2 for my x-intercept on the right. However, it only crosses the x-axis twice. One time it touches, and then one time it cuts through. Okay, and you have to say x-axis carefully, otherwise it sounds like something that we would not want to say, okay, especially to children. Sketching the graph of factored polynomial, state the degree. Okay, so degree on this question is, let's see here, we have x to the third times x squared. So this is x to the fifth. So this is a fifth degree polynomial, okay? List the zeros. Okay, zeros would be -2 and +1. Now, how do I know that? Look at the factors and set the factors equal to 0 and solve, right? Now, I say that, I hope that this, it makes sense that you're setting them equal to 0 and solving. That's how you end up with those, but if that doesn't make sense, state the multiplicities. You know what? I should do a better job of writing out the zeros and the multiplicities. What if I did zeros and multiplicities, made like a little table? So the zeros were -2 and 1. -2 had a multiplicity of 3, right? And 1 had a multiplicity of 2. Okay, so we should be seeing an odd multiplicity and an even multiplicity. Okay, and this one's going to have the bounce, and this one's, the other one is going to cut through the axis. Axis, gee whiz. Man, got to be careful, can't go fast through these descriptions. And you got a -2 over here, and we got a +1. Since it's got a leading coefficient of +1, we know the right end behavior is up. Since we know that we're talking about an odd degree, we know that the other side is opposite. Now, the -2 is the one that cuts through the axis. And the bounce occurs over here. Now, the truth of the matter is, if you take a look at your graphing calculator, you're probably going to see something that looks more like this. It's probably going to slice through the axis like this and then bounce. It's almost like right here it would be doing like an x cubed thing, since it's being raised to the third power. So if you look at the picture on that one, you might end up with something that looks a little bit more like that versus just slicing right through the graph. Okay, so we have the basic idea. Okay, the using the intermediate value theorem. Okay, the intermediate value theorem, hold on a second. Okay, so this intermediate value theorem, it's really kind of important. It's a big deal when it gets to calculus, because what you're saying, and I'll explain why, if you've got, if A and B are real numbers, A is smaller than B, and the graph has to be continuous, that's extremely important. The function has to be continuous on the interval from A to B, including both ends. The f, the function, has to take on every value between. Now, notice those are y values. In other words, you have to have every number in between. Now, why is that important to me? Well, what happens if you've got negative values here and positive values here? Well, guess what has to happen in between? You have to have a y value of 0 somewhere in between. So if you've got positive y's and negative y's, then that means you had to have crossed the x-axis in between. Explain why a polynomial function of odd degree has at least one real 0. Well, it's got opposite end behavior. It has to go through the axis at least one time. The even degree functions have the possibility of never crossing the x-axis because they go in the same direction. I could actually have one that does something like this, where all the y values are negative or all the y values are positive, and you never have that positive on one side, negative on the other, and end up having to cross somewhere in between. And folks, it doesn't mean that I am over here. I could have everything over here. It just means that I have negative y's and positive y's So it must mean I have to have 0 somewhere in between. Now, I'm not really going to try to trick you like this, but there are situations where I could, right here, you might think that it's only hitting the x-axis one time, but if you zoom in, there's actually 1, 2, 3 that are right in here, and then 1 over here. That's kind of mean. I mean, I'm not going to try to do that to you. That's cruel and unusual, and I don't think that's right. Okay, and that's enough notes for today, I think. Hold on a second. Let me look and see what we have left. These are the questions that we'll be working on in class tomorrow, or on Wednesday. So, I mean, you can get started on some of them, but I wouldn't knock myself out. You know, we'll be practicing together and seeing if there are things that we can learn together on this. So, that's it. Talk to you later. Have a great day.